Hey guys, welcome to our online revision program for Excel at Science, Excel at Maths. Winter is here and so are your exams. And so what we thought we'd do is bomb through a few topics online and give you some input, some hints and tips, and some examples to go through along with some practice material. So what I'd like to do with you first is vertical projectile motion. Okay, so we're going to go quite fast. There's a lot to cover, but I'm not going to try and teach it from scratch. I'm just going to hit some of the key points and some of the ways that you should approach a question, do an example with you, and then it's over to you for some practice. Okay, so first thing we're going to have a look at is freefall. What is freefall? Well, it's things that skydivers do. If you've ever done that, it's great fun. Freefall is basically where the only force acting on an object is gravity. That's the phrase to look for, where the only force acting on an object is gravity. So the ball, or whatever the object is, can be going up or down. It's still freefall. If you were to put it in a diagram, free fall is the object with the only force acting on it being gravity. Okay, and that is the sort of setting for all the scenarios that you're going to meet in the various different calculation questions. And there's bound to be one. It's usually question 3, roundabout in your exams. Right at the get-go, they send you into vertical projectile motion. So what I want to do to give an introduction to the way that the questions might be worded, there's kind of 4 main scenarios that you might meet. So let's quickly run through them as to what the object might be doing. Okay, so let's just have a look at it like this. Number 1. There we go. The first scenario is quite simple. It's just the object being dropped from a particular point. So it travels from A to B. Simple as that. And because it's been dropped, what do we know about the initial velocity? Yes. Sorry, kidding. Initial velocity, obviously, when it's dropped, is initial velocity is 0. So that really helps in calculations where you don't have to worry about the VI values. And if you look at the equations, actually quite a few of them have a factor with VI in it, and so your maths becomes quite simple. The second scenario, reasonably similar. The object is still going from A to B, essentially. But this time, instead of being dropped, the object is thrown down. So it does, in fact, have an initial velocity that you have to take into account in your calculations. Pretty simple so far. Third scenario, we now have a look at an object that goes up and then comes back down to where it started. So for the first time, we need to think more carefully about, well, where is this object in its journey and how much of the journey has it done? So you see these A's, B's, and C's. I often do that in my diagrams just for my own reference, really, so that I can clearly identify different points, key points in the journey, and make it absolutely 100% clear in my head what I'm dealing with. For example, in this particular question, you could have little Johnny walking along and he throws a ball up into the air and he catches it 4 seconds later, you're told. And the question then asks, well, how high did the ball go? It's pretty strong, as you'll see, but basically, if you could throw it and keep it in the air for 4 seconds, you wanting to try and find the height, can you use the 4 seconds directly to find the height? Well, answer is no, because the 4 seconds relates all the way from A to C. It's the entire journey. If we're wanting to find the height, that is only A to B. So therefore, in your calculations, you would have to say, well, the full T equals half. We're going to use a delta T of just 2 seconds. Okay, so that's the kind of thing where you have to now be a little bit careful about which values you're using. Let's just finish this little table to see how we would go about doing this question. We're trying to find H, which is our delta Y, effectively. That's our thing to find out. What are the other key pieces of information to know? Velocities, well, we don't know how fast he threw it, but we do know how fast it was going at the top, because always at the point when it turns around, the velocity is going to be 0. So we can say VF is 0 meters per second. And then the other thing that's always true for our free fall scenario, remember, only force acting on the object is gravity. Therefore, A is going to be equal to g. So our acceleration is going to be 9.8 meters per second squared. Now, before we go any further, quick little check. Which way are we going to make positive? I'm going to come back to this in a moment, but this is so important because it can wipe out your marks very quickly if you don't think about this one. I would normally take, in an instance where the ball is traveling up, to make up positive, but that's not a rule, it's a guideline, and as long as you stick to whatever you've chosen, you're 100% fine. So if this was the case like that, then I would have to make acceleration minus 9.8. Okay. We've got t, we've got our distance, we've got final velocity, we've got a. We're doing good. We don't need the initial velocity because we've got enough to put into an equation. So I'm going to leave that there, and let's move on to the fourth scenario, where perhaps you've got something being thrown up off a building and then it goes past where it started all the way down to the bottom. So it's kind of like the scenario 3, except it goes beyond point C all the way down to perhaps point D. Okay. Same approach. Just think very carefully which way I'm going to make positive, which part of the journey am I looking for, and so on. Let me just throw in one other scenario that you might get. It's kind of like a bonus feature. These ones all have in common that they have just one object. Okay. This one here is where they introduce potentially two objects. So for example, let's say we've got someone standing up on top of a building and they drop a ball down to the ground, whilst someone else on the ground at the same time throws up a ball, and at some point they pass each other in the air. And you're being asked, well, how long did that take before they passed each other, or at what height were they? Now, you're in a difficult scenario here because you don't have enough information with either ball to find out the answer. So you have to take both of them through the calculations to a point where you can't go any further, and then bring them together. Simultaneous equations. So whenever you get a double body, double ball, double object scenario, you're going to be dealing with simultaneous equations. Okay, so that's a little hint. Those are the basic scenarios that you're quite likely to meet in your exams. So let's quickly now look at how you would approach a question. We've essentially done a little bit here already, but just to clarify some of your key points. There's a technique that some of you may have been privileged to learn about at Excel at Science over the years, and that's called REFWA. For those who haven't, ask your tutor next time you're in, please teach me about REFWA because my life is not complete. But a key part about REFWA, sorry about the bashing in the background, the key part to REFWA is it's when you're approaching a question that you're doing it systematically. And the early stage of processing a question is often really difficult, especially for these sort of matric style questions, is that you read it through and you think, oh my gosh, where do I begin? And this is where REFWA is extremely helpful. And a key part, I'm just going to give you a snippet of REFWA today, and it's the E, E stands for extract in REFWA. And it's about extracting the information from the question and getting it all organized so that when you run it through your calculations, everything's fine. You don't end up putting, I often use a cooking analogy, and it's like, well, if you're making a chicken casserole or a chicken curry or something like that, you don't just take the whole chicken and just chuck it in the pot. You've got to prepare it. You've got to put it on the chopping board and get it in the right sizes and so on. So in the same way, when you get given the question, you don't just pick a formula and just go for it. You have to check that you've got the right units, that you're using the right quantities, that it's plus, minus, all that kind of stuff. So one of the things that really helps with that is what I call the 3D approach. So quickly run through that, the 3Ds, what they are. Okay, here's all 3Ds. The first D is a diagram. This is for mechanics questions especially. Every single mechanics question that you get, momentum, work, energy, power, vertical projectile motion, forces, whatever it is, there's always a diagram that you can draw. Now sometimes you can take a little bit of a shortcut and just embellish the one that's on the paper, but I strongly recommend that you do a diagram. Okay. it helps for you mostly to visualize what's going on, to be able to recognize, well, where does this start? Where does it finish? What part of the journey am I looking at? Or whatever the key facts are. So diagram is first, and then kind of linked to that, they should go sort of hand in hand in your approach. Can you see that? Maybe I'll make these darker. Is, as I said just now, direction. It's a sneaky little one, but it's so important, because if you don't get your direction right, then all your vectors are a bit precarious. And remember, vectors come all over the place. It's force, it's momentum, it's velocities, it's acceleration. They all are vectors, and so direction is fundamentally important. And you will not believe how many people lose marks there because of the biggest tsotsi in science, and that is the minus sign. Watch out for the minus sign, it will rob you blind, right? So watch out for the pluses and minuses, make sure that you get your direction properly organized. I'll go through an example just now, make more sense. Third thing, once you've got your diagram, your direction, then your third D, double colors now, your third D is to put all your data in a list. Okay, and that list is, as I was saying with the sort of cooking analogy, it's where you get all your ingredients laid out, organized, and ready to put into the pot, which is the formula. There you go, you can see how it all ties together now. So that's the 3D approach. I'm going to use that approach in tackling a particular exam question so that you can get a feel for how it works. It's from November 2011, and it's a good old hot air balloon question. Okay, so remember the 3 Ds: diagram, direction, data. Don't ever not do it. Okay, so question, it's in your workshop booklet, so you can read along. A hot air balloon is moving vertically upwards at a constant speed. A camera is accidentally dropped from the balloon at a height of 92.4 meters, as shown in the diagram below. The camera strikes the ground after 6 seconds. Ignore the effects of friction. And the diagram. At the instant the camera is dropped, it moves upwards. Give a reason for this observation. That's 3.1. Okay, so let's just read it through again. I'll just work through systematically. A hot air balloon is moving vertically upwards at a constant speed. Quite a helpful thing, by the way, when you're reading through questions, and this is part of the whole RefWorth thing, by the way, is read with a pencil or a pen or a highlighter or something so that you can underline key facts so that they stand out to you. So hot air balloon is moving vertically upwards at a constant speed. Important, underline that, constant speed. The camera is accidentally dropped from the balloon at a height of, underline, 92.4 meters, as shown in the diagram below. The camera strikes the ground after, underline, 6 seconds. Ignore the effects of friction. So we've been given some stats and some facts. Let's draw our own little diagram just whilst we're getting our head around it. So it doesn't have to be a Picasso style diagram. There's our hot air balloon, there's our camera. It's going to go up and then down to the ground. Okay, that's what we're going to deal with for now. And at 3.1, they are asking us, at the instant the camera is dropped, it moves upwards. Give a reason for this observation. Okay, so 1 marker. So there's a few different approaches. The key word that should come to your mind relates to Newton's first law, which can be summed up with a word beginning with I, and that is inertia. The characteristic of mass to want to keep doing what it is doing already. If it's stationary, it wants to stay stationary. If it's moving, it wants to keep moving. So because the camera was moving up already, well, it wants to keep moving up. Okay, so that's the sort of the heart of it. What you could do to relate it to the scenario, to the balloon scenario, is to say something like VI of camera, I'm just going to write in shorthand here, is initially the same as the velocity of the balloon, hot air balloon. Due to inertia. Or so it continues going upwards due to inertia, something along those lines. You're going to get the memo for this as well, by the way. Okay, so that's just a one marker. By the way, I hope you're getting used to the fact that in your final exam you've got 150 minutes to do in 3 hours. That's 150 marks to do in 180 minutes. So a minute a mark is a good guideline for you to go on with the department exams. Okay, minute a mark, it gives you about half an hour spare at the end to check things or a bit of buffer. So there we go, that was a minute, more than a minute on that. 3.2, calculate the speed VI at which the balloon is rising when the camera is dropped. Okay, so they were giving you a little bit of a help by already calling it VI, and you're in the right direction there. So we've got to find this VI. Before we go any further, I'm just going to do my little trick of, let's just make sure we're looking at the right part of the journey here. A, where it started, B at the top, let's call C where it got to back where it's the same height as where it began, and D where it gets to the ground. Now, facts that we're given, let's start putting a list together. We know that the height at which it was dropped from was 92.4 meters. I've drawn my diagram. Before I start putting any data together, point number 2 of 3D is direction. Okay? So diagram, direction, let's choose our directions. I'm going to choose upwards as positive. As I said, you can choose whatever you want, but just be consistent, must flow through the whole question. We're going to be working towards VI. That's going to be our ultimate conclusion. But before you put in the rest of the information, and we're considering direction and so on, I would suggest that you put at the top of the table or a little note somewhere as to which part of the journey we are considering. I've kind of given it away as to which part of the journey I would suggest we consider. The reason that I've chosen A to D, not just to the top or back to where it came from, is because that's where we've got the information. If you think about this distance, 92.4, that is the distance that it's traveled all the way from A to D. Also, the time that we were given, 6 seconds, is the entire journey, A to D. So rather than choosing just a part of the journey, I'm going to stick to the whole thing, and let's put some of those values in. So the time elapsed was 6 seconds. Here's a key one now, the displacement we're dealing with, not just distance, displacement, I'm going to call it delta y because we were in vertical. It's gone from A to D. In other words, it's traveled down. So it has to be minus 92.4 meters. Key point there. The acceleration, as we know, is g, and that's also downward, so it's minus 9.8 meters per second squared. Okay. So there's some facts and stats. We don't need the final velocity. We're just being asked to find the initial velocity. So let's plug those into our equation. You have a look through your formula sheet, and the one that's going to work with this bunch of values, this is like choosing, you've got all your ingredients and you know what you're going to cook, choosing the right pot, okay? The pot that has all of those ingredients ready to rock and roll is delta y equals VI delta t plus half a delta t squared. Now, don't forget that this is a fundamental part of starting every calculation, partly because you're going to get marks for it, also because it sets you off in the right direction. So let's sub in our values, and I'd suggest just keep everything in the format that you've laid it out and just plug the values in. Okay, so here we go. So delta y is minus 92.4. VI is what we're trying to find. Delta t is 6. Plus a half minus 9.8, 6 squared. Okay? Now we can begin to simplify. My suggestions of how you simplify are you get everything except your unknown all on the one side, so that what you see is pretty much what you put into your calculator. It's a lovely check to avoid any silly calculator errors or mental errors. Like you could, some of you are more brainy and more flexible in your mathematical gymnastics in your brain. You could do that in your head, but don't fool yourself that you're not going to make mistakes in an exam. Okay, so let's do some rearranging. By the way, good news is you've probably got about 75% of the marks already. This next step is literally not rewarded in science. It is in math, but not in science. It's just getting things in the right order. So let's perhaps bring this across to the other side, and then we're going to take the 6 underneath. So just to avoid too much confusion, I'm not going to flip it around. I'm going to keep VI on the right. We've got our minus 92.4 minus, because I'm bringing it over, a half minus 9.86 squared, all over 6. Does that make sense? Okay. So then our initial velocity is, let's get a calculator, and as I said, it should be fairly straightforward because what I see is what I plug in. So let's make a fraction, minus 92.4 minus 0.5 times by minus 9.8 times by 6 squared over 6 equals 14. Nice round number as well. So it's encouraging. How do you present that? If in doubt, you can put 2 decimal places. Because it's a round number, you don't necessarily need to worry about that. So in this case, I would probably just put VI equals 14 meters per second. And remembering that it's a vector, we must also include upwards. I always underline my answers, make it nice and easy for the examiner to know when I'm done. And that's it. Okay, so that's 3.2, 4 marks done and dusted. Let's keep going. 3.3 is a sketch graph. Probably should have left my diagram there to refer to. Anyway, let's go on now. So, let's read the question. Draw a sketch graph of velocity versus time for the entire motion of the camera. Indicate the following on the graph: initial velocity, time at which it reaches the ground. Another 4 marker. So just to recap, we're drawing a sketch graph and line of velocity versus time. Okay, so we're plotting V versus T. As you can see, I've drawn positive and negative, anticipating that it can go both ways, as we know this object does. Indicate on the following on the graph: initial velocity and the time when it reaches the ground. So I would suggest draw your graph, your initial graph in pencil. You can always go over it in pen when you're 100% confident. But let's have a look and see what we've got here. So this is our velocity, that's our 0 velocity. We worked out that it's going up at 14 when it initially goes off. So let's put that value in. There's 14, that's going to be our initial point. Now, which way is it going to go? Well, we threw it that the camera was going up, and was it speeding up or slowing down? Well, we know it was slowing down to 0 when it got to the top. So what we expect the graph to do is to go down to 0, and because it's going down at a constant rate due to constant acceleration, it's a straight line. So we're expecting it to do that. Okay. When it gets to the top, the ball then turns around and starts to come down. Be careful though, it doesn't mean that your graph then turns around and bounces back up again. Okay? Because what's happening now is the velocity is now in a downwards direction, which, as we know, let's put a little thing here, direction indicator, downwards is negative. So the graph actually just continues downwards and actually would go beyond whatever 14 was, because it goes past where it started, and it would go down somewhere like that. Now, they haven't asked you for a specific velocity, but what they have asked you to do is to indicate when it stops, and that was at 6 seconds. So don't forget, because we've got values on those axes, you must put units, and that's kind of where the marks all lie. It's not just drawing the graph, it's getting appropriate labels and units, the correct shape of graph, the correct values, etc., etc. So that's what that one would look like. If you got it upside down, as long as you put your values in correctly, you'll be fine. All right, and then the last question, it's a 5 marker. If a jogger 10 meters away from point P, as shown in the above diagram, and running at a constant speed of 2 meters per second, sees the camera at the same instant it starts falling from the balloon, Will he be able to catch the camera before it strikes the ground? Use a calculation to show how you arrived at the answer, 5 marks. This is a present on a plate. Okay, let's go through it again. A jogger, 10 meters away from point P. That point P is where it hits the ground, yeah? And he starts running at a constant speed of 2 meters per second. He sees the camera at the same instant it starts falling from the balloon. Will he be able to catch the camera before it strikes the ground? Okay, so we need to do a little calculation also to show how we came to our conclusion. Now, we need to match up the jogger's motion and his time to the camera's motion and time and compare the two. That's where we're headed. We've got the camera already, 6 seconds. That's how long it's going to take. Can the jogger get there in time? Dun, 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 dun. So let's have a look at the jogger's motion. Let's make a little list for him. Well, his velocity is 2 meters per second, or her velocity. Say him there? Anyway. And the distance, delta x, is 10 meters. Now there's a bunch of different equations you could use using all the equations of motion, but bear in mind this is a constant velocity, so we actually don't have to worry about a VI and a VF and an acceleration and all that sort of stuff. All we're interested in knowing is what's the time going to be. So you can go back to your grade 10 equation for velocity, where you could write it as velocity is delta x over delta t, perhaps. Velocity is the change in displacement per unit time. Let's just sub in the values. Here we go. So v is 2, x is 10, and there's our t. Switch it around. Delta t is 10 over 2, which equals 5 seconds. For your interest, here's the marks. 1, 2, 3, 4 marks out of 5 already, just for that. Unbelievably awesome. Okay, and then the last thing you need to get that 5th mark is just to say, yes, 5 is less than 6. 5 seconds is less than 6 seconds. Therefore, he will be able to catch it. He'll be able to. Whether he will or not is another question. Whether he sort of butterfingers, oh, I'm trying to catch a camera that's falling from 90 meters. It's like a 30-story building. Anyway, on that note, I shall leave you to practice your own vertical projectile motion questions. Good luck. Ciao.